Welcome to Indeed, and thank you for taking the time out of your evening to join us for these Tech Talks. I'm Donal McMahon, and I'm the Director of Data Science. I've been here for 2 years. This evening, I'm going to speak about how you can make your products better, using science as a process, mathematics as the tool, and data as the raw ingredient. Specifically, I'm going to convince you to use the scientific method as your framework to make your product decisions. This will help your team with a common vernacular, a common process, and that will lead to consistent outcomes. And then I'll teach you how by stepping through some real examples. As we've seen a couple of times tonight, we help people get jobs. We wear lots of t-shirts about it as well. And we pride ourselves on the fact that we've used data for many years to help people get jobs as well. It's woven into the very fabric of all of our business decisions. It's why I came to Indeed. We were data-driven before it was cool. And so much so, we've actually given 6 tech talks on it, 8 if you count tonight. And it's covered a variety of areas. We talked about logging data. We've talked about interactive analysis. We've spoken about the pitfalls that one can easily encounter if you do data-driven in an incorrect manner. We've even spoken about product design and how that can be well-informed by data. Okay, everyone's following us. And part of that is due to the explosion of data itself, and part of it is that we've been successful, as have other data-driven companies. So we've inspired companies in the healthcare industry, in television marketing, in data-driven HR analytics, and even as far as dining. Every day I see one of these headlines, and it's really exciting, but it's also a little bit frightening. And there are many good reasons why you should be data-driven. Firstly, it democratizes decision-making. No longer is it the highest paid person in the room, the loudest voice in the room, or the most intransigent person that gets their way. It's the data that helps to decide. If you believe in the wisdom of crowds, and if you believe that more participation leads to better decisions, you'll find that data-driven approaches and a data-driven business model will be successful for you. By allowing the independence for your teams, by giving them a scope to use the data to draw inference themselves, you actually also increase the decision velocity. We've removed ego, we've removed opinion from the process, so now it's pretty collaborative. It's fun. It's fun to work with data, and it's fun where you're talking objectively about things with others. I had an epiphany a couple of months ago. I realized that data-driven isn't an accurate descriptor for what we do. Data is a raw material. And Caden already spoke about this, but it isn't a way you make decisions. It's just part of that decision-making process. We're actually science-driven. And you should be science-driven too. And I'll try to convince you of this through a cautionary tale of how I failed, and I failed badly. So this is a picture of not me and the PM, but a figurative representation of us. A couple of years ago, we were dreaming big. We were about to change the world. We were about to help job seekers. We noticed one little thing. We saw that people were using the mobile device more and more to apply for jobs. Great. What do we do? Well, we came up with a simple idea. Let's modernize our mobile UI. Let's make the Jobseeker experience awesome there, and therefore, people will use it more. Pretty simple. On the left here, you see the UI at that time. Okay, so it's pretty good. And this is our control group. And then we worked with a designer to come up with this. And it looks beautiful. Once we'd finished congratulating ourselves and patting ourselves on the back, we started to think about, well, what did we actually change? We changed 4 different things. Firstly, we increased the spacing, the white spacing between each of the jobs. It's much more spread out. Secondly, we actually we replaced this orange text with on the new and apply with your Indeed resume with these little buttons, far slicker. We actually got rid of sponsored jobs, and we just used the organic content. And lastly, we actually had a bunch of minor tweaks on the UI. The button for home, we replaced where it's had text before, we have an icon. We also got rid of the salary range and just had one single number. And we had other font changes on top of that. So we changed everything at the same time. We were so happy. Oh my word, we were so smug. We We convinced, we evangelized, we advocated for this, and we convinced the software developers to actually implement it with us. And that was not a trivial amount of work. And we ran A/B tests. We generated lots and lots of data. And we love A/B tests. We analyzed them separately. And we got completely opposite answers. Trouble kind of began. And we started to scratch our heads about that. And we thought, well, why are we getting opposite answers? And the answer was really simple. We hadn't defined concepts in an identical fashion. When we talked about Jobseeker Experience earlier, well, what is that? What's a positive Jobseeker Experience? What's a negative one? And how do you even measure it? What's a job? I know it sounds silly, but I thought I defined a job to be anything that appeared anywhere on the mobile search page. The PM correctly pointed out it should be only those jobs that were visible to the job seeker before they made the decision. What's an acceptable metric trade-off? And this is probably the fundamental question tonight. Every time anyone here has ever run a UI experiment, they've noticed that you move clicks around. You give visual prominence, you give visual space for different units. And so you're making trade-offs all the time. And so you need to define what is an acceptable positive trade-off for job seekers and what is one which is not acceptable and is negative. And we thought, OK, we're data-driven at Indeed. Let's be more data-driven. That's the solution here. And we threw more data at each other. We sent more and more emails. And we started to speak about weird ideas like first principles. A little bit of a tip, if you hear anyone ever mention first principles, shout BS. We wasted time. We got frustrated. We actually got really angry. And it was horrible. And it really boiled down to the fact that we had different hypotheses when we started. We had different data. We were actually looking at slightly different versions of the data. We had different metrics. We had nothing defined commonly. And we just drew different conclusions. It was inevitable. Thankfully, at Indeed, it's OK. Failure is OK sometimes. You just need to learn from it. And so we learned an important lesson. We learned that it's not sufficient to be data-driven. You need a process around that. And you need that process still to retain all of those virtues of the data-driven ethos. There is a solution. It's not a utopian ideal. It's actually got a pretty good track record. And it's called the scientific method. Many of you will remember this from your elementary school days, but you will typically start with an observation about the world as it is today. What is your nature as it is today? Secondly, you'll start to ask big, profound questions about that nature. Then you'll get into hypotheses, narrower, testable ideas. You'll think about what you can measure and how you'll measure what will be your success. Then you'll experiment, run analysis on those experiments, and draw inference or conclusions. With those conclusions, you actually inform your next set of observations. And in that way, you can iteratively learn and improve your product. For the remainder of this talk, I'm going to speak more and more about that mobile UI experiment. It's pretty embarrassing, but I'm going to talk about that failure extensively. I'm going to talk about what we did, why it was wrong, and how you can do it better. So stage one, observation. What does that actually look like? Or what did it look like for us? Nothing. We did nothing. We were brilliant. We came with ideas. We'd solved the problem. We didn't even question what the reality was. And this is wrong in many, many ways. Just pick the top two here. We didn't establish a baseline for what Jobseeker Experience was. We didn't know what positive was. We didn't know what negative was. We definitely did not know how to measure it. When we failed, and we did, we had no knowledge to actually build upon thereafter. For us, we had no way that we could learn and inspire future work for the team. And OK, here's how you can do it better. And I've separated these out into 3 different aspects. There's the nano level, right in the blood and guts of this. That's where you study real job seeker sessions. People often forget to do that. I'll speak more about that in a moment. Secondly, at the macro level, use the experts you have in your company. The user experience team or user experience researchers you have spend all day, every day, thinking about the problems that job seekers have. They've accumulated high-fidelity, qualitative data. And you should work with them to think about how you solve problems for real job seekers. Then you need to scale it. Okay? It's okay having that high quality data in low volumes, but you need to scale it because you're going to inevitably run an A/B test at scale, and so you need to be able to measure when you've been successful, and you need to be able to measure when you've missed. So I would encourage each and every one of you to spend at least 2 hours when you start a project looking at real user sessions. Not alone are they different than what you think they are, they're different in weird and wonderful ways. People are using your product today in ways you didn't imagine. It's weird, it's interesting. And so you should do that at the start of any project you're working on, the middle, and at the end. You'll learn an awful lot. You do it as a team. It's the best exercise you can go through. So what happens in a user session at Indeed? Well, firstly, maybe a job seeker comes in and they issue a query. Truck driver in Boulder, Colorado. They clicked on the first job. 2 minutes later, they clicked on the third job on the page. And then they disappeared for 20 minutes. And they came back and they then queried taxi driver in Boulder, Colorado. They saw the fourth job and they applied for it. So now you've actually got a bit of context. You know what that user is doing. You can see what they're trying to do. And that context matters a lot. As I mentioned already, you just can't even imagine how people are using your product today. Your preconceived notions, I promise you, are incorrect. OK, up to micro. And this is where we gather high-fidelity qualitative data. And this is a shameless plug for Robin Rapp and Vicky Zhang, 2 members of our team. They wrote a great blog post about this recently. Go check it out. And in it, they talk about how to use qualitative data to inform the features you select for a sales lead generation machine learning model. In it, they speak about 3 different aspects. 1, sitting next to the sales representatives and seeing how they do it today, how they choose good leads and bad leads in that process. Then they ask them why. Why are you doing this? What past experiences have informed this behavior? Lastly, now they have information about a small group. Let's see if the patterns they notice there actually are consistent with a larger group. And that's where you run surveys. There's a lot going on. There's a lot of great literature out there about large-scale data analysis, and you should go check it out. If you want references, come talk to me. But I'm going to talk about a new idea, and that's observation via experimentation. The most common question I get asked all the time is, come up with the perfect objective function. Come up with that perfect metric, and it'll solve all our problems. We'll be all done, and we won't need a data science team anymore. The reality of it is you've kind of already chosen it. Remember I spoke earlier about the fact that every UI experiment is a trade-off. Your product today is actually a trade-off in your values. You just have to learn what that trade-off you've decided implicitly is. You should learn it through experimentation. It's cheap. You can run lots of them, and they're pretty trivial. And you can be learning all the time. And I'll show you how in a moment, what that actually looks like. And these are, I term them perturbation experiments, and they should be the simplest experiments that you can start in 5 to 10 minutes. Imagine our 2 metrics are job alert signups and applies or applications. Your current state is the following. You know how many applies you get from your product. You know how many job alert signups you have. Great. That's helpful. That's a good starting point. But it doesn't tell us what we could achieve. What are the feasible changes that we could have? And that's important because any new big launch that you propose, any new change to your mobile UI, you need to be able to put that in context of whether it's a good trade-off versus what you could get cheaply via simple experimentation. So how do we do that? Let's run simple experiments. Let's just bold the apply with Indeed resume text. We'll get more applies. We'll lose out on some job alerts. We could add a pixel to the job alert UI. It's going to make it more visually prominent. You probably get more signups for the job alert apply, but you'll lose out on job alert signups, but you'll lose out on applies. And this way, you can construct a whole set of these experiments, and you can construct with each of these data points referring to one of those experiments. So you have an idea of what's going on. Let's talk about Pareto efficiency again. Okay, you actually have 4 Pareto efficient alternatives to your current state. They define your implicit trade-offs. Let's talk about one of them and see what that looks like. Here you have the delta in applies. You have the delta in job alerts. With this and the other 3 Pareto efficient alternatives, you can now start to state things like this. Each new job alert sign-up is worth 1.7 applies to us. And in this manner, as you run more and more of these perturbation experiments, you can become more and more confident of statements like this. That's the end of the observation stage. Let's start thinking about how we form big, important research questions. Yeah, there's the cat again. We did nothing. We were just so smart. Oh, and it was wrong in a lot of ways. We actually never prioritized the most important questions. I mean, if you think about it, if you're a product manager, an engineer, a data scientist, you always go through these weekly exercises of prioritizing tasks. But when we started this project, we didn't even bother with that. The biggest investment we made, we didn't prioritize. We bundled questions together. We bundled all of those changes in one treatment. And so when we failed, we actually couldn't tell, and even if we had succeeded, we couldn't have told which of those were actually important. And I want to introduce you to a particularly useless character who's called Captain Hindsight, who points out all of the mistakes after you've made them. And so I'm going today to try avoid being Captain Hindsight, but I'm going to say how you can do it better. What's a good research question versus a non-worthwhile research question? I'd propose 3 metrics here. One is the potential impact you could have, the complexity for implementation, and the amount of time it takes to learn from that. Our product landscape is really competitive, and so you need to be launching good features and helping to meet job seeker needs in an iterative fashion all the time. And so here are 3 proposed research questions we could have come up with. What are good measures for job seeker experience? Embarrassingly, we never asked that one. Secondly, how can we help job seekers navigate more quickly to their chosen job? And thirdly, how can we clearly denote sponsored content? They're all worthwhile, important questions. And then we have to narrow them. We have to go from the research question stage into the hypothesis formulation stage. This is the largest section tonight, and we're going to go into a lot of detail about many of the aspects here. So please bear with me. That's not a hypothesis. Modernizing the mobile interface to improve job seeker experience. That's like an ideal, a vague ideal, as Captain Hindsight points out. We didn't have established metrics. We didn't even have established data we're going to measure with. And we didn't have a clear success or failure criteria. You can do it better, and this is a proposal how you would. Here's a simple single hypothesis you could check. Does extra white space between job cards help job seekers navigate more quickly to their chosen job? That's a hypothesis. That's testable. And the metrics you might choose to measure that, I'm going to propose 3 of them, and I'll tell you why 3 in a minute. But they might be time to click, click-through rate, time to hire. Okay, on to the how many metrics. And Caden spoke a little bit about this earlier. He gave 3 to 4. But I wasn't satisfied with that answer. I wanted to make sure there was some math behind it and it had some actual principle. Okay, sorry, Kate. So your product is a high-dimensional hypercube. What do I mean by that? You can measure your product in many, many ways. Thousands of ways, possibly hundreds of thousands of ways, if you log everything like we do. Here's a 2-dimensional hypercube. It looks like a diamond. Here's a 3-dimensional hypercube. You now see a cube. 4-dimensional, starting to get a little bit more complicated looking. When we get up to 7 dimensions, it's a mess. It's really difficult to understand what's going on. And imagine this in thousands and thousands of dimensions. You couldn't use that to make product decisions. And so we need to reduce it down to a lower dimensional space which retains almost all of the information that's in that high-dimensional hypercube. There's actually a well-established set of tools in signal processing and statistics to do exactly this, and it's called singular value decomposition. And I apologize, Mr. Chase, or President Ford. There will be math. And it goes along the following. And so it's OK if you tune out if you're not a data scientist right now or a mathematician, but this is fun. and I couldn't resist including it. So imagine your hypercube is A here, which is n by p dimensions. You can say, and this is, excuse me, I should introduce singular value decomposition. It's a generalization of eigendecomposition for positive semi-definite matrices. I'm sure that helps. And so you actually pull out as much of the signal as you can into the U and the V components here. These are orthonormal matrices with orthonormal columns, and you leave what's left, and this is the important part, is that S. That's the vector. And each of those singular values actually, in of themselves, tell you how much signal you have in each of the dimensions. And by looking at them, you can say, well, how many dimensions retain almost all of the information? This has been researched extensively, and here's a great paper on it from Gavish and Donahoe. And the answer is essentially 3 to 4. So lots of work, and we got the same answer, but I'm feeling more confident about it now. OK, so the second question is actually, how do you choose good metrics? There's a whole academic discipline dedicated to this, point estimation, and some of us kind of dedicated our 20s to this. Look how young, look how happy I was. look how sunburnt I was. OK, so more seriously, though, choosing your metric, you need to think about what you're actually aiming for in the first place. Many people start with the things that are easy to measure. That doesn't mean they're things that matter. And this is, I'm going to refer to this as your estimand or your target. You want to hit that bullseye. You need to think about how you're going to hit that target, and that's your your estimators or your estimates. And that's your theta hat. And there are 3 mathematical criteria that are well established for how you actually trade off and determine whether a metric is good or not. It's bias, variance, and then the third of those, OK, this is new, this is system complexity. And let's talk about bias. Really straightforward concept. It's how far away your estimates are from your actual estimand. The closer you get, obviously, the better. This is the mathematical formula for it. This tells you that we want to look at the distance between your estimates and your estimand in expectation. And it's really easy to miss bias. Bias comes in lots of different forms. You can have selection bias and how your data was generated. You can have metric bias. You can have experimentation bias. We only ever experiment on things we care about. And you can have publication bias. If you ever read the journals, you'll find that only positive results are published. There was a hidden bias in our example, and we missed it. It was estimating the time to hire. I spoke about this metric earlier, and this was for job seekers. And this is our data. Here you see that we had n job seekers. Their first action was between the 1st of January 2016 and the 23rd of April 2016. This is false data, sorry. Still active. This tells us whether the job seeker was still searching by the end of our study. And some of them were hired, some of them weren't. And so we see the dates on which they were hired. OK, so we thought about it a little bit, and we said, OK, we have hired data for a portion of our data. Let's find the average time to hire for those who were hired. Oops. Yeah, exactly. Oops. Yeah, so we've a second Liam Neeson in the audience. There's a flaw. We only thought about, of these 5 job seekers, we only thought about 2 of them and incorporated them into our metric. We didn't think about all of those job seekers who either didn't get a job or we didn't have visibility into them, whether they did or did not get a job. So there was also another different type of selection bias in here, in that some of these job seekers stopped searching on Indeed. They may have got a job, they may not. We may not have known. They may have got a job on a different site. And lastly, all of these job seekers started at different times. And so if we'd ran our study for a week, we'd only have ever measured hires which happened between time 0 and time 7. And if we'd run it for longer, we'd get hires which had a longer duration. So our metric is flawed in many ways. But there's a way to do it. It's called a Kaplan-Meier. And that's a way to give you an unbiased estimate of typical time to hire, and I'll tell you how. And let me talk you through this. I think this is important, and I think you'll like it. H hat t is the estimated probability of being hired by a given time t. How can you get at that? Well, let's think about the time 0 to time 1. We have a certain number of people who were available and searching at that time, and we'll term them n sub I. Then we have a certain number of them who actually got hired at that time, and that's h sub I. The probability that nobody was hired in that time would be 1 minus h1 over n1. And if we do this consecutively for time 0 to 1, time 1 to 2, time 2 to 3, and so on, we actually get an estimate of being hired by time t. And it looks like this. It's the blue step function that we see here. And this is, just to be clear, this is 1 minus ht. This is the chance that you weren't hired by time t. And so nobody was hired at time 0, so it's 1. Some got hired at time 1, time 2, and so on. And so we've actually estimated at any given time how many people we thought would be hired from our original population. The red step functions you see on either side, or orange, they actually explain, they give you the confidence interval around those estimates. And so we're back to our original question. What's the typical time to hire? It's really easy. You look at 50%. What's the median time to hire? And we get an estimate of about 7 units of time. We have a confidence interval as well on that. It goes somewhere between 4 and 11. Okay, so that's bias, and that's how you might adjust for bias. Let's think about variance now and why that's important. Here's a visualization of what variance actually looks like in practice. Here's low variance and slightly higher variance. So it's the spread of data around your estimand. Here's the mathematical formulation of that. Here we see our estimate, theta hat, and our center of our estimates, which should be the estimand itself if we're unbiased. And we see that it's the square of the difference between the two of those, the sum of the squares. And it's really fundamental for valid statistical inference. An old manager of mine used to say that the only thing that data scientists know that software engineers don't know is variance. It's as simple as that. Science assumes that we're innocent until proven guilty. It says nature is the way it is today until you have evidence to disprove that. And that's our null hypothesis. Nature is the way it is today. And you need to prove that beyond reasonable doubt. How do we actually quantify doubt? Well, variance is your quantification of doubt. That brings us to, well, okay, we've got variance, we've got bias. How do we combine them to come up with a good estimate? Most of the time, it's pretty straightforward. Pick your class of unbiased estimators and pick the one which minimizes the variance. Lets you come out most quickly with your conclusion. But that's not always the case. Especially in machine learning, we often start to think about trading off the top right here, high variance, low bias, against high bias but low variance. That's actually a fundamental concept in machine learning, and people refer to it as the bias-variance trade-off. There are many good reasons for that, usually around generalization and understandability of your models. So we've talked about bias, variance, and now let's think about system complexity, and this is really difficult. Caton's whole talk was essentially, I think, speaking about system complexity and how you can best understand and quantify that. Product development isn't linear. Sometimes you have multiple targets you could aim for, and you don't really care which one you hit as long as you're hitting one of them and being really close to the bullseye on it. Sometimes you have a target that's partially blocked. A good example of this is in e-commerce where you have conversion tracking only for a certain proportion of your job seekers, or sorry, of your users. And so you have a biased view on the data you get. Sometimes you don't even know that bias. It keeps moving all the time. It's a competitive landscape, and it's really, really stressful. Okay, so let's think about how we could quantify that and what sort of model we could come up with it. Sadly, I don't think there is one. I think it's all context specific. And I think you need to ponder that, and you need to come up with a suitable solution for that context. And it doesn't let you off the hook. Just because it's tough, it doesn't actually let you off the hook. You still have to think about it and factor it into your decisions. Caton spoke about the funnel earlier, and I think I can't add much more than the great ideas he had there. So I'm going to talk about March Madness. Okay. Yeah, I know, it's kind of funny, isn't it? The Irish person talking about March Madness. It's a really strange American staple. For anyone here who doesn't know about it, it's every March, 64 or 68 college basketball teams get together, and they play this single elimination tournament to determine the national champions. It's really weird. It's kind of like the FA Cup for Americans. Okay, so there's actually a game within the game. And this is why, sorry, I didn't really introduce this. System complexity is really important in these brackets and in the way that people play these games. So what do I mean by that? Well, here's a bracket. The game within the game is you predict who's going to win. People get together in small groups or large and make predictions on all 63 of these games. You have, each of the teams are ranked, and you have to predict who's going to win each of those. I'm not really good at this, so I predicted an upset in the first game and in the second, and I was really wrong. But the point is, you get rewarded for getting these games or these outcomes correct, and I got one of them wrong. And as you go further into the tournament, if you got one wrong at the start, if you predicted an upset at the start and got it wrong, like I did, then you'd actually see that those errors are compounded as you go further and further into the tournament. So what's the system complexity here? Okay, there are 3 factors I think that are really important to think about if you were coming up with a metric or a strategy. One is that you have downstream compounded loss, and you should account for that in your loss function. You have the number of bracket participants. If you're only playing with 3 people, go with the favorites. You're probably going to win out. But if you have a lot of participants, well, then you need to take chances. You need to go with some upsets in the hope that you're right and you win. If there are a different number of points awarded at different stages, well, then that will reward your risk-taking behavior. And all of these lessons actually apply to product development as well. Okay. I'm sure most of you are trying to think, well, actually, how can I win my NCAA pool next year? It's really simple. You do some Markov chain Monte Carlo simulation, look at any of the actions that could happen, simulate them downstream, and see if how that affects your win or non-win probability. You can come talk to me if you want to see a model for that. It's fun. Okay. So this was a big section, the hypothesis formulation. And so let's kind of bring back what we've actually learned. Okay. Firstly, specify your hypothesis really clearly. Have 3 metrics, and make sure those metrics don't have a lot of bias, have as little variance as possible, and they account for your system complexity. Use sensitivity and correlation, as Caton spoke about earlier. They're great measures of system complexity. Brings us to experimentation. What did we do? Yeah. We ran a single experiment where we changed everything. And so, again, thank you, Captain Hindsight. He's always around. You couldn't disentangle the effects of the 4 different treatments. We didn't know whether the positive and negative experience our job seekers were having was due to the fact we had white space there, that we changed the salary estimates, that we changed the color of the text. We just didn't know. And you can run a full factorial experiment to do this better. And it's possible. It's really easy. Imagine our 3 experiments were the following. A, where we had white space, extra white space, or not white space. B, where we had orange text or we changed it to the buttons. C, where we had salary range or single points. Okay, so what's going on? There's a lot going on in this visualization, so let me take a minute. Okay, so you start here. On all of those, you have your control group. It lies in the bottom left-hand corner. You can change your A is vertical, your B is horizontal, or your C is depth. Okay, and so you run 8 variants here. A pro tip is make your control a little bit larger. That will give you extra statistical power. But in this way, we actually can look at all of the linear effects and all of the combined effects of all of these changes at the same time while running it on the same amount of traffic we would have with just that single variant. It's kind of statistical magic. So what does it buy you? Well, it gets you increased statistical power, so you have to run your tests for a shorter period. You get a simultaneous testing of all of the effects, and you see all of their interactions as well. In common parlance, you learn more and you'll learn it more quickly. Analysis. Stage 5 of the scientific method. We're nearly there. What did we do? We spent an inordinate amount of time on this. This is where we spent 90% of our effort and time. We put data together from multiple places. We defined different metrics. Some of them had the same name, click-through rate, but we defined what were impressions differently, remember. We invested a lot of time in analyzing these tests, and it didn't really get us anywhere. It's too late at this stage. You shouldn't invest your time into analysis. You should be investing your time in the 4 previous stages: observation, questions, hypothesis formulation, and experimentation. If you've got to this point and you're inventing your analysis, you're too late. It was horrible. And this should have been trivial. It should have been simply plug and chug. Let me explain why. You have 2 different things you can change, in essence. You have your product. You can make a new product or just have a product intervention, a new feature. You can have your existing metric or data. You can have new metrics or data. If you did the first of these, it's uninteresting. You know about your existing metrics. You know about your existing product. If you do the second of these, where you just change your metric, you actually have, this is a great time for data or metric innovation. Product innovation, like the mobile UI experiment, should have been this. We should have used existing well-understood metrics to check our changes. We didn't, unfortunately. We tried this. We tried to change our metrics. We tried to change our product. And so we learned nothing. So never use new data or metrics to validate new products. Brings us to the last stage, and this is the conclusion stage, and this is where you draw inference from all of the work you've done before. We drew 2 different conclusions, so we had no conclusion. And this had really important implications. We didn't learn anything, and more importantly, we lost the trust of the software developers, the user experience team. Nobody wanted to work with us anymore because we had no credibility. But you can do better. And again, this is not the time for innovation. This should follow directly from your analysis. Good science doesn't involve innovation at this stage. If you're innovative, you're data peaking, you're data mining, and you're accumulating scientific debt. Okay, here's a new one. It's called the Goldilocks syndrome, and we all fall into this all the time when we look at A/B tests. Imagine you run an A/B test, and you see an outcome in your metric of choice. It can go all the way from -infinity all the way up to +infinity, and everything in between. Let's think about the first 3 of these. These are the negative, all the way from terribly negative to mildly negative. What conclusion would you draw? And what conclusion do we generally draw? We'd say it's too cold. We say, oh, it's probably because we have a bug, and we look hard for that bug at that stage. Because our idea couldn't be broken, it must be a bug. We segment users. We spend a lot of time understanding that. It could be too hot. If it's really positive change, we're also suspicious, and probably rightfully so. We should be skeptical. It's probably a bug. This is just right, though. This is where we declare victory. We never question. Don't ever question these, because write it down in your quarterly evaluation slide and move on. You've had a big victory. And it's bad science. It's pretty obviously bad science, but we do it. We all fall into this trap. So don't be Goldilocks. Retain healthy skepticism. Always be positive about it, but be skeptical. Always look for bugs, even if it's 2% win. And check for repeatability. How do you do this? You run a holdback. As you scale up your test that looks great, actually hold back 5 or 10% of your traffic and confirm that what you saw in your initial test is still present once you've made that your new product feature the largest proportion of the job seeker or user experiences. That's really important. Often you'll find that what you'd measured in small tests is not the same as when you ramped it up to 95% of your traffic. Okay, so we're kind of at the end of this, the scientific method. We've gone through each of these stages, and let's have a quick recap. For the observation stage, think nano, micro, macro. For the question stage, this is really important. Actually prioritize this. Create a backlog. Beware of implicit trade-offs. Find ways to make them explicit. At the hypothesis stage, well, it's really important to think 3 metrics, and then evaluate them using bias variance and system complexity as best you can. The experiment, you have to consider the way you set up your experiment. You'll get out of it that which you invest in construction and design. Full factorial experiments, they work almost all the time. Analysis, this should be trivial. If you're spending time on this, you've invested incorrectly. It's not the time for data innovation, and beware of the Goldilocks syndrome. Always check for repeatability of any results that you have. We live in a data-rich or a data-abundant era. It's really cheap to run holdbacks. It's really cheap to run experiments. Use that to your advantage. Okay, so be happy. Use the scientific process. Get ice cream like we did tonight. Okay, so I'm going to leave you with a few thoughts that are hopefully not too controversial and you'll be convinced of. But don't be disoriented by the amount of data you have. You need to have a process to consume it. I would propose that the scientific method is that process. Lastly, invest in the early stages of the scientific method. That's where you'll actually get the greatest reward, and you'll thank me later. Okay. Thank you very much for your attention, and we'll finish with that.